Oh, dude, I wrote that on my paper.
Okay.
Don't say that.
Guys. So today's actually really kind of short and sweet. Going to talk about differentials, and really it's kind of a goofy thing.
Wow. Way to disrupt the class, bro.
Linearization, though, is kind of a big deal, but it's a really simple one. Using tangent lines to approximate a curve, it only works in the immediate vicinity of the point. The idea is if you zoom in close enough on any curve, what do you get? You get a straight line. So you can use a tangent line to approximate a curve. Okay? It's one of the things that we do.
What does that mean by approximate?
So, okay, let's say in the equation that I have to work with, the curve itself, the equation itself is difficult to handle. Okay? But I can use a straight line. It's much easier to work with. She's not here. She actually already got it.
Okay.
I hope so, because I marked her absence though, so I need to know if she's here or not. If she is. The idea is that sometimes curves can be really hard to work with, but straight lines are easy.
Yeah.
Right? And that's what we do is because a curve, and I say curve, an equation that that's not straight, can be often difficult to work with. But if we zoom in close enough, what do we get? We get a straight line. So we can work with a line to approximate what's going on. That's actually kind of what we're doing when we use differentials to find the slope of a curve. Because you can't find the slope of a curve, but you can find the slope of the tangent line at that point. Because the tangent line and the curve, if you zoom in close enough, will be the same thing. The idea is using derivatives in order to find a straight line, to find the tangent line. That's what we're doing. The linearization is basically what is the tangent line at a particular point, and using that tangent line to approximate what's going on with the curve. So the example I have here is that suppose the f of x equals negative x squared plus 4. Find the linearization at a equals 1, and use it to estimate f of x at x equals 1.1. So the first thing we need to do is you find the tangent line. That's just another form of a tangent line. It's actually the point slope form of a line, or sorry, yeah, the point slope form of a line with the y-coordinate moved to the other side. So the linearization of x is f of a. Well, a is what in this case? A is 1. So I want to find f of a. I plug in 1 into f of x. So 1 squared is 1, negative, so you get negative 1 plus 4, that's 3. Plus f prime of a, our slope, the derivative of that, put it over here, f prime of x is negative 2x. Plug in 1, what's our slope? Negative 2 times x minus a, x minus 1. And then you want to clean it up to get a nice straight line. Okay? But that's point slope formula, right? X coordinate, y coordinate, slope. That's what that is. Clean it up. Negative 2x plus 5. Is that right? Yeah. Negative 2x plus 5. So this is x. This is f of x here. This is L of x.
So L of x
is the tangent line. It's the linearization. Now, and then use f1.1. So what is the linearization of 1.1? Okay, so I plug in 1.1 for x. Negative 2 times 1.1 plus 5. 2.1, 2.2, negative 2.2. So I end up getting 2.8. And the idea of this is I have this straight line, and I've got over here, this is where 1 is. Right here, this is the point 1, 1. Actually, it's 1, 3. Okay. If I move off a little bit, just a hair, 1.1, I can use the tangent line rather than the actual curve. because I'm fairly close, because right here, they may not be exactly the same, but the difference between the curve and the straight line is minimal. If I'm 1/10 of away from where they intersect, particularly with just the parabola, they are essentially the same. They're not exactly the same, but they're really close. And which would you rather do? Take -2 times 1.1 and add 5. You can do that really easy. Or you can take 1.1 and square it, make that negative, and subtract it from 4. It's not hard, but it's not, you know, it's kind of the idea behind it. Depends upon the equation you're dealing with. The linearization is very much easier to work with than the actual equation you're working with. Other ones, not so much. But you do have to remember, linearization is only accurate when you're very close to the point of tangency. If I move out to 2, okay, that is not going to be a good estimate. Using the straight line to estimate what that is at 2 isn't going to be a very good estimate. But as long as I'm right nearby, it's okay. And it's interesting that one of the things that we don't get into here, it's actually in your book, but we don't get to that portion of your book. But if you were to take second semester or do the DC, they actually do use derivatives to come up with a polynomial to estimate a curve with, which is much more accurate if you can get a curve that looks like a curve rather than a straight line. So it's accurate for a little bit closer. And you can actually get a fairly accurate polynomial within a certain range. Well, that is one of the things that you do is you actually, rather than coming up with a straight line approximation, you come up with a polynomial approximation. So you can match a curve with another curve. Even more accurate. Okay. That's linearization. That's it. Come up with a tangent line, use that tangent line to expand. This is extremely popular with AP. They love to use this. They love to have you write the linearization. They love to have you write the tangent line and then use the tangent line to approximate the value of the equation at a certain point. They love to do this. You see it almost every single year now at some point in the AP test. It's one of the ones they really started pushing more and more often. Differentials. This really, I don't see much other than the book, but it's actually kind of a nice thing to look at. The idea is to use the differential to estimate the change in y to go with your change in x. And I like this because it's a real lead-in to what we're going to be talking about tomorrow or Wednesday. Okay. What you're actually trying to do, what did dy and dx stand for? dy is actually delta y and dx is actually delta x, and delta stands for the change. So how does the change in y relate to the change in x? If I change x, what does that do to my y? That's the idea behind this equation, to kind of study this. I like this because that's exactly what we're dealing with on Wednesday is related rates, which is how does one thing changing affect the changing of another thing. That's the idea behind this. So it's really a lot simpler than it looks. Okay, it says find the differential dy, then evaluate it for x equals 2 and dx equals 0.5. So you take the derivative. That's what it is. The derivative of y is dy. The derivative of x cubed plus 12x is 3x squared plus 12 dx. That's it. It's doing the derivative. dy and dx. And then evaluate it for x equals 2 and dy equals negative 0.5. So at the point, if I'm at the point 2, where x equals 2, and I change my x coordinate 0.05, negative 0.05, if I go from 2 to 1.95, what does my y change? That's what this question is asking me. If I go from 2 to 1.95, how much does my y change? And I don't know where the y is, but I can find out how much it changes. That's what this tells me. So dy equals 3 times 2 squared plus 12 times negative 0.05. And rig out the calculator here. 3 times 4 plus 12, so that's 24, right? Right, because 2 squared is 4, 4 times 3 is 12, 12 plus 12 is 24, so 24 times 0.05, negative 0.05, yeah. So what is dy? Negative 1.2.
That's all that is.
Yeah. So if I'm at the point 2, whatever, if my x-coordinate's at 2 and I move from the x-coordinate from 2 to 1.95, how much does my y-coordinate change? And it changes negative 1.2. A lot of change in y for a little bit of a change in x. That's all this is doing. This is relating the change in one part of your coordinate with another part of your coordinate. What is the actual change? Well, you can always just plug the numbers in and figure it out anyways. But I like this because it talks about how one thing changes the relationship to another. Yes?
So like you compare these.
Yeah. That's all you're doing is you're just doing a comparison. But the idea, remember, calculus is the mathematics of change. That's what it's designed for, to measure change, to evaluate change. How fast is something changing? How slow is something changing? What we're doing now is we're relating the change in one thing to the change in something else. I change x. How does y change to go with it? That's what this does. It introduces that topic that we're going to, like I said, we're going to discuss in much more detail coming up. So, do this one. Okay. So first thing you need to do is you need to take the derivative. dy equals 2 secant squared of 2x dx. Chain rule, you have to have the 2. Okay. And then evaluate that for x equals pi and dx equals 0.1. So dy is equal to 2 times the secant squared of 2 pi times 0.1. So the secant of 2 pi, secant's 1 over the cosine. Cosine of 2 pi is 1. So that's 1 squared, so that's 1 squared. Times 2 is 2. Times 0.1 is 0.2. Questions? So if my equation is the tangent of 2x, and at the point x equals pi, if I move to pi plus 0.1, my y-coordinate moves 0.2. Now the change in 1 affects the change in something else. Okay. This is a real big preview to Wednesday. Now, you notice I have a shade. You're not expected to do everything on this one. However, I do want you to do the first one. So the radius of the circle increases from 10 meters to 10.1 meters. So it's expanding. I've spilled a barrel of oil, and I've got a circular puddle spreading. How much does the area change when the radius changes? What's the change in the area compared to the change in the radius? As it's expanding, as the radius goes from 10 meters to 10.1 meters, how fast is the area changing? Or I should say, what is the change in area? So, first step is take the derivative. Okay? So dA, the derivative of the area, is equal to the derivative of pi r squared in relationship to r. So this would be 2 pi r dr, rdr. That's the first part. Okay, if r equals 10 and dr equals 1, the change represents the change in radius from 10 to 10.1. So if I plug it in, if I plug in 10 and the change in area is 2 pi. So I change 1/10 of a meter from 10 meters to 10.1. My area changes 2 pi square meters. Okay, the true change. Okay. The true change is delta A. So if I take the area when it is at 10.1 meters, subtract what it was at 10 meters, okay, I end up getting my change, if I factor out the pi, square 10.1, square 10, and then you redistribute the pi and you find the difference between the two, dA is 2 pi. The error, how much I'm actually off by, is 0.1 pi, 0.01 pi. That's actually pretty accurate. My estimate, because dA is just an estimate. What I found in the first part, 2 pi was an estimated change. What is my estimated change in radius, or change in area? Well, I'm estimating that my change in area is 2 pi. How much was I off by? 0.01 pi. So I was off by about 300ths of a square meter. That's not that much. That's like that. Okay, that's not a very far angle for something that's 10 meters across. 10 meters is a lot. I was off by about that much. Okay, so you can get a fairly accurate estimation this way. Okay, what's it going to do? If it expands, what's it going to do? You can use this for predictions and such. Okay, and then the last part is just kind of throw in the approximate percentage change in area can be found, and that's the approximate change in area. I don't get hung up on that last part. But what I want to do, like I said, okay, today's lesson, the big deal, okay, is linearization. Okay, the first part is the part you're going to actually really use more than anything else, is that linearization. We only did one, but really you've done tangent lines before. All linearization is what's the tangent line? Find the tangent line and use the tangent line to estimate what my change would be if I moved over a little bit. Okay, that's all that is. Use the straight line to approximate your curve. This other stuff, I view it more as an intro to the concepts we're going to deal with on Wednesday. Realistically. Okay. You'll have a few homework problems, but I didn't give a lot of homework problems with it, and it will just be very close to what we're going to be doing starting on Wednesday. Okay.